This video seeks to discuss how to reduce the concentration of greenhouse gases from power plant emissions through carbon dioxide capture and coal gasification. Our specific focus is the capture of carbon dioxide from coal power plants, as they are huge contributors to the issue. Over 25% of greenhouse gases are produced from electricity generation alone, and 30% are produced from transportation. There has been a drastic increase in the Earth's average temperature over the past 20 years. Carbon dioxide is the most abundant greenhouse gas produced and emitted by industries, which severely damages the environment and leads to ozone depletion. In order to reduce emissions, power plants should switch to coal gasification with CO2 capture, as it is a cleaner method of producing power. Coal gasification is a process that converts carbonaceous materials such as coal, petroleum, or biomass into gas using gas-solid reactions. The product is a synthetic gas known as syngas that contains carbon dioxide, carbon monoxide, hydrogen gas, nitrogen gas, and methane. The coal gasification industry purifies the syngas and burns it to generate power in a more environmentally friendly way. The efficiency of syngas to produce power is largely dependent on its composition, especially the purity of its combustible compounds such as hydrogen gas. Coal gasification implements a spray dryer reactor in its process line to remove non-combustible carbon dioxide from the syngas. This in turn improves the efficiency and significantly reduces the amount of carbon dioxide released into the atmosphere.
The carbon dioxide in syngas reacts with aqueous sodium hydroxide in a spray dryer to form solid sodium carbonate and water. The major product is solid sodium carbonate that can be collected to provide another source for revenue. For this reaction, a catalyst is not being used due to the fact that it would introduce another side reaction for an undesirable product, as well as favor the rate for that side reaction. This project used a pilot study in order to set a basis for the overall scale. This pilot size reaction was then scaled to the optimum size for the reaction parameters in the MATLAB code that will be discussed in depth later in the presentation. The scale-up factor was found by finding the average emission of carbon dioxide from a coal gasification plant and using that emission as the incoming flow rate of the carbon dioxide in the syngas.
On this slide is a collection of figures created from the MATLAB code and represents the trend which led to the final reactor specifications and operating parameters. Figure 1 shows that as the molar flow rate of carbon dioxide levels drop with spacetime, the molar flow rate of water vapor increases before reaching a plateau around 0.15 minutes. Because water vapor is the only gaseous product of the desired reaction, it becomes a major component of the exiting gas stream. The second figure shows the generation rate of the two solids precipitating out of the dryer when carbon dioxide reacts with aqueous sodium hydroxide. With the increase of spacetime, the rate of the desired solid is much greater than the undesired solid, leading to a higher production of the more valuable product, sodium carbonate. The third figure shows a relationship between the selectivity of the two solid products with a sharp initial increase followed by a plateau. Further increases in spacetime and thus reactor volume will not lead to any increases in selectivity. Figure 4 shows the relationship between the temperature and the desired and undesired reaction rates. At temperatures below 190 Kelvin, the undesired reaction rate produces sodium bicarbonate in a larger amount than the desired product, sodium carbonate. Though increases in temperature increase the reaction rate and the selectivity of the desired product, high temperatures will also limit the extent of the reaction between the carbon dioxide and the sodium hydroxide. This, in effect, will reduce the amount of carbon dioxide captured by the reactor. For this reason, a syngas feed temperature of 400 Kelvin was chosen. Figure 5 shows how the nozzle diameter and the approach temperature parameter affects the desired reaction rate. Decreasing the size of the nozzle will produce a smaller droplet of aqueous sodium hydroxide and thus increase the surface area to volume ratio of that droplet. As the surface area increases, more carbon dioxide can react, thus increasing the reaction rate. The approach temperature parameter represents the temperature difference between the adiabatic saturation temperature of the syngas feed and the reactor itself. A peak can be seen in the approach temperature parameter, which was chosen to be the value used in the optimizations. In Figure 6, the concentration of aqueous sodium hydroxide was altered to find the values which corresponds to the maximum desired reaction rate. The plot shows that a peak value was found, and any further increases in concentration only benefits the side reaction over the desired reaction. With the operating parameters of 400 Kelvin for a syngas feed, 10 ATM, and 100% of the syngas feed run through the reactor, a final reactor volume of 1,930.8 cubic meters was found to be optimum. 310,386 metric tons per year of carbon dioxide is projected to be consumed, correlating to a conversion of 98.96%. From the energy balance calculations, 7.2 kilowatts of energy is needed to heat the reactor above the inlet syngas temperature.
The projected economic impact for an investor of a carbon capture in a coal gasification plant is also very promising. With a first-year profit of just under $92 million without factoring in employee wages and maintenance fees, this business has great potential. The average lifespan of a coal gasification plant is approximately 20 years, and the graph on this slide shows that the 20-year earnings of the plant far outweigh the initial investment cost of the reactor and the first bulk batch of 2 molar NaOH. By being able to produce energy using cleaner methods, the harmful environmental impacts from greenhouse gas emissions can be reduced. Further development of this process can lead to more sustainable industry. Moreover, the additional income from sales of sodium carbonate can be allocated towards research and design.
For this project, MATLAB was used to calculate the reactor specifications and operating parameters based on the user inputs. The first section of the code represents the preset values of syngas concentration and the standard total flow rate from pre-built coal gasification plants. These values are inputted to the reactor flow values function, which calculates the mass, molar, and volumetric flow rates entering the reactor. These values are then sent to a script file to calculate the values of concentration for each species. The concentrations are then sent to the ordinary differential equation function. The ODE function uses the desired and undesired reaction equation to find the molar flow rates and the molar generation rates for each species in the reactor. These values are exported to the script file and used to create the first 2 figures. The optimum value for spacetime was found when the derivative of the figure 1's curve dropped below 0.1% of the inlet carbon dioxide concentration. The values of selectivity plotted in the third figure are calculated instantaneously from the vectors created in the ODE functions of the desired and undesired solids. The fourth figure was created by 2 ranges of independent variables, the approach temperature parameter and the nozzle diameter. These matrix calculations were plotted to create a 3D surface plot showing the optimum values for each variable. The optimum concentration of aqueous sodium hydroxide was found by calculating the desired rate of reaction using a range of concentrations and plotted to find the maximum. This section of the code calculates the total amount of CO2 captured, desired and undesired products formed, the conversion of CO2 in the spray dryer, and the exit mole fractions of the purified stream. This next section of code is used for the energy balance calculation for the conversion of CO2 in the spray dryer. Using the species value listed in the report, a CO2 conversion of 97.36% was obtained. The final section of this code shows the financial calculations used to find the projected profits of the coal gasification plant over the next 20 years. When we run this code, we will be asked for 3 user inputs which will alter the reactor specification and operating parameters. In this demonstration, we will use the optimized values found in the slideshow of 100%, 10 ATM, and 400 Kelvin. When running the code, all 7 figures show up, as well as the calculations used in the report. These calculations are for the specific reactor chosen by the user inputs and also list the best operating parameters. Thank you for watching, and we hope you enjoyed this presentation.